I want to begin our discussion now of two- and three-dimensional motion. This is very much related to one-dimensional motion, except now we're going to work in more than one dimension. And it's important that you understand that the second and third dimension are independent of the first dimension. So if they're independent of the first dimension, what are they dependent on? And that's time. So let's revisit the whole concept of position and displacement. So here is the position of an object. We're going to define the position as some location R. This is with respect to some origin that we can designate as we see fit. And the object will have an X position, a Y position, and a Z position, which I might subscript as R sub X, R sub Y, and R sub Z, or I might just use X, Y, and Z. And each of these respective positions is multiplied by its respective unit vector I, J, and K. For the most part, I'll use the X, Y, Z position. Now it's important that we understand that position is a function of time. So time is the independent variable, and then the position will be the dependent variable. So X doesn't depend on Y, and Y doesn't depend on X. Both of these depend on time. So position is the dependent variable. And this is generally the format that I'll use here. R is a function of time. That's what this is saying right here. Position is a function of time. And the X position is a function of time, and we multiply that by the X unit vector I hat. Y is a function of time, and we multiply that by the J unit vector. And Z is a function of time, and we multiply that by the Z unit vector K hat. Displacement, then, is the change in position. This is the same as it was earlier on. So it's the new position R2 minus the old position R1. Alright, so new position minus old position will be the displacement of some particle. So this is the early time, or I'll say the earlier time, and this is the later time. And again, both are functions of time. In mathematics, you'll learn about this. If you haven't already, this is referred to as a parametric equation. So what you have are 3 or 4 variables that are functions of another variable, and we generally designate that t. In physics, t stands for time. In mathematics, it's just whatever that independent variable is. Here's the position of an object in the xy plane. Y is measured in meters, x is measured in meters. Is this path across which this object travels a function? Now, you may recall the vertical line test way back in the day in mathematics. And the vertical line test said if a vertical line passes through a relationship in more than one location, then it's not a function. But you got to remember that when we did that, y was a function of x. That's not the case here. We don't have y as a function of x. In this case, y is a function of time, x is a function of time. So this is in fact a function. The position of this object changes with respect to time, and at no one time is the object in 2 locations. So the vertical line test would have said at this position x, y has a value here and here. That is to say, at one x point, the function of x has 2 different values. And so what that means in physics is that at one time, the position of the function has 2 different values, meaning you're in 2 places at one time. That's not what we're working with here. This is a function of time, not a function of x. And so the vertical line test does not apply. So this is a function of time. So let's pretend that you start at this location. So this is R1. And then you move along this green path until you reach a later location. And I'll just choose this one right here. And we'll call this location R2. So R1 equals -4 in the I direction plus 6 in the J direction, and that's in meters. And R2 equals 7 in the I direction minus 5 in the J direction, and that's also meters. So the displacement delta R is equal to R2 minus R1. And so that displacement would be 7I minus 5J meters, that's R2, minus -4I plus 6J meters, which is 7 minus a minus 4, that's equal to 11, that's in the I direction, and minus 5 minus 6, that's equal to minus 11 in the J direction. And so the displacement, delta r, is 11I minus 11j meters. So the displacement vector is from here to there. Well, if I look at that, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 meters to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 meters down. And so indeed this delta r, this displacement, is 11I minus 11j meters. So when I go to look at average instantaneous velocity, remember average velocity is the change in position over the change in time. And so if the time it took to travel from R1 to R2 was 4 seconds, then my average velocity by definition would be 11I minus 11j meters divided by 4 seconds, which is 2.75 I minus 2.75 j meters per second. That's the average velocity of that path. The instantaneous velocity, on the other hand, is defined as the derivative of position with respect to time. So I could write it this way: derivative of r with respect to time. Again, 3 bars in my equal sign means this is a definition. This is always, always, always true. Well, you know from calculus that the derivative of a sum, in this case x is a function of time I, plus y is a function of time j, plus z is a function of time k. That's a sum. And so the derivative of the sum is the sum of the derivatives. So I take the derivative of the x position with respect to time, multiply by I hat. The y position with respect to time, take the derivative of that, multiply by j hat. And the derivative of the z position with respect to time, multiplied by k hat. Another way that physicists will note a time derivative, so I don't have to write all of this every time, is with this dot notation. So x dot means the derivative of x with respect to time. Y dot means the derivative of y with respect to time. Z dot means the derivative of z with respect to time. Now if I'm walking along a path like this black path you see here, then my velocity is always tangent to the path. The direction points in the direction of motion, and it's always tangent to the path. Now remember what that means. Tangent means that the line touches there at only one point, and so the velocity is in that direction. Over here, the velocity is touching at one location. It's in that direction. Now I might move from R1 to R2 just like I did earlier. This would be the displacement. And so if I take this R2 minus R1 and I divide that by a change in time, this would be an average velocity, not an instantaneous velocity. An instantaneous velocity is always tangent to the curve. So if I go back to the previous slide, then my instantaneous velocity is there. Over here my instantaneous velocity is there. At this location my instantaneous velocity is there. And I might be getting faster or slower. So since velocity is always tangent to the curve, if I'm driving along this path, my headlights will always point in the direction of my velocity, unless I put it in reverse. If I want to change my speed, then my speed is the gas pedal or the brake. That's going to change my speed. If I want to change my direction, change the direction of this vector from here to here, in order to do that I have to use the steering wheel. So the steering wheel changes the direction of the velocity vector. The gas pedal or the brake changes the magnitude of the velocity vector. Well, remember that a change in velocity is an acceleration. So acceleration is, by definition, the derivative of the velocity vector with respect to time. So that's the derivative of the x component with respect to time in the I hat direction, plus the derivative of the y component with respect to time in the j hat direction, plus the derivative of the z component with respect to time in the k hat direction. And when I go back to my dot notation, remember that v sub x is equal to x dot. And so this acceleration would be the derivative of the velocity in the x direction with respect to time, but that's equal to the derivative of x dot with respect to time So that's x dot dot. So my acceleration is just the second derivative of the x position, which I'll write out as x double dot. It's just notation. That's the same as this times I hat plus the second derivative of y with respect to time. That's y double dot times j hat plus the second derivative of z with respect to time times k hat. That's instantaneous acceleration in 3 dimensions. The average acceleration would just be the change in the velocity vector over the change in time. So this would be A average. It's also a vector quantity. Don't forget these are vector quantities. That's very important. A classic example of two-dimensional motion is the projectile motion. Now in projectile motion, as an example, you might have, say, a golf ball that's being hit off of a slight hill, and the golf ball is going to follow this red path until it reaches the green and lands on the green somewhere near the hole. So let's assume that I hit the golf ball with some initial velocity v0, and v0 is a magnitude, but the velocity is at some angle generally measured with respect to the horizontal. Not always, but most often v0 will be measured with respect to the horizontal. So when I do a problem like this, the first thing I want to do is set up my coordinate system. So I've got this ball on a hill and it's heading towards the flag. So I'm going to set up a y-axis and an x-axis. Now I can put the x-axis either at the landing point or I could put it where the ball starts. It doesn't really matter. I'm going to put it at the landing point just for the sake of having something set up. So there's my x and my y. So that's my coordinate system. That means that the ball is here at some initial x, which happens to be 0 because that's the way I've set it up, and some initial y, which I'll call y0. And so this is the initial position of the ball. Then the ball has some velocity, initial velocity v0, coming off at an angle theta with respect to the horizontal. So what I'm going to want to do is take that velocity and break it up into its components. I'm going to take the acceleration, I'm going to break it up into its components. So the velocity has some speed v0, and it's going to have an x component, and that's going to be the cosine of theta. Because remember that v0 is the magnitude of this velocity, and it's at an angle theta with respect to the horizontal. So this component is adjacent to the angle theta, and that's the horizontal component, or the x component. So v0 sub x equals v0 cosine theta. That's the initial x velocity. And then there's an initial y velocity, and that's going to be the opposite side of the angle theta. And so v0 in the y direction is equal to v0 sine theta. Now if the ball were shot down, then v0 would be in the fourth quadrant, and the y component would be negative. So be careful of your signs. The only acceleration in this problem is the acceleration due to gravity, and that's in the downward direction. So g is in the minus j hat direction. That's the only acceleration. So this is the acceleration in the y. There is no acceleration in the x. And therefore, since there's no acceleration in the x, that means the x component of the speed, or the velocity, is not going to change. So this remains that value all the time. So the x component is v0 cosine theta, and the y component is v0 sine theta. Again, that's only because theta is measured with respect to the horizontal. If theta were measured with respect to the vertical, you'd have to make some changes here. So be very careful about where theta is measured and in what direction the velocity is taking place. So now that I've got my accelerations and my velocities, I'm ready to write out my equations. Now remember, x and y are completely independent of each other. And I'm working in a situation where I have a constant acceleration. And it's the acceleration due to gravity, and that's constant. And so my x position is equal to x0 plus v0 t plus 1/2 a t squared. You remember that equation from one-dimensional motion. But now I've got a y equation as well. So y equals y0 plus v0 t plus 1/2 a t squared. But we have to remember there's components here now. So my velocity v0 is an x component in this equation, and my acceleration is the x component in that equation. But recall from the previous slide, there is no acceleration in the x direction, so that's 0. Then the y component over here of the velocity must be v naught in the y, and the acceleration due to gravity is minus g in the y direction. Minus because it points down. And if we go back to my coordinate system, you'll see that the coordinate system says positive y is pointing up. So I can rewrite this as x equals x naught plus v0 cosine theta t, and y equals y naught plus v0 sine theta t minus 1/2 gt squared. So keep in mind the negative sign of gravity pointing down is already accounted for in this equation. So y equals y naught plus v0 sine theta t minus 1/2 gt squared. So don't put negative 9.8 in here because it's already accounted for right there. So the acceleration g is just going to be 9.8. The minus sign, the downward direction, is already accounted for. I can also use v naught squared plus 2a delta x equals v squared. That equation still holds, but keep in mind I've got to use the x component, and the x component. And over here I would use the same thing but with y components. In many problems they'll talk to you about the maximum height and the maximum range of a projectile, and in general these are only going to be discussed when the final position and the initial position are at the same height. In other words, I'm shooting a projectile over level ground. So if I come off with some angle theta, and I have some speed v naught, and I'm interested in the maximum position, when that happens, then my y goes from 0, if this is my coordinate axis, to 0. And so I could write 0 equals 0, final position in the y direction equals initial position in the y direction, plus v naught in the y direction t minus 1/2 gt squared. Or 0 equals v naught sine theta t minus 1/2 gt squared. But I can do some factoring here. I can take that t out, and I'm going to get 0 equals v naught sine theta minus 1/2 gt times t. Now you'll notice there's two solutions for this. One of them is t is equal to 0. Well, of course, that's right here at the very initial point. What I'm really interested in is the time it takes to get to there. And so that's going to happen when this whole thing in parentheses is 0. And so v naught sine theta equals 1/2 gt. When I solve that for t, I get 2 v naught sine theta over g is equal to t. So that's the time it takes to go from here to here along this path. Now I might be interested in then, what's the maximum height? Well, remember symmetry. What goes up must come down. And so if this is the time it takes to get all the way across this path, the time it takes to get to maximum height, that's going to happen right in the middle. Again, if my starting point and my ending point are at the same level. The time it takes to get the middle is going to be half of that. So t top must equal v naught sine theta over g. So t at the top equals v naught sine theta over g, and I'm interested in what is that height. Well, there's two ways of doing this, the hard way and the easy way. I'm interested in what's that y value. Well, that's going to equal y naught, but that's 0, plus v naught sine theta t minus 1/2 gt squared. And all I have to do is take this value of time and plug it in here and here. Now that's the hard way, because first off I've got to square it, and there's going to be kind of a mess, but let's do it the hard way. So I get y equals v naught sine theta times t, but that's v naught sine theta over g, minus 1/2 gt squared, but that's v naught sine theta over g squared. But that's equal to v naught squared sine squared theta over g minus 1/2 g v naught squared sine squared theta over g squared. But the g's cancel, and I get v naught squared sine squared theta over g minus 1/2 of that, and that's just going to be 1/2 v naught squared sine squared theta over g. So that works out just fine. But the easy way would be to take a look at this problem and think, how long does it take to go from here to there? Well, up here, the y component of the velocity is 0. So I'm just basically dropping the ball straight down. So from what height? So y equals 1/2 gt squared. That's the maximum height from here down to the ground. There is no velocity starting at the top going down to the ground. And it's the same amount of time. So I get 1/2 g v0 sine theta over g quantity squared, but that's just exactly what I have right there. So this is equal to y max. Now what about the range? This is referred to as the range. How far have I gone in that time period? Again, we use this time right here. So the distance I've traveled in the x direction, so r is equal to x0, but that's 0, plus v0 cosine theta times the time. But the time is 2 v0 sine theta over g, plus 1/2 the acceleration times t squared. But there is no acceleration in the x direction. A sub x is equal to 0. Super important. A sub x is equal to 0. So this is it. So I get v0 times 2. That's going to be squared because there's a v0 and there's a v0. Then I have cosine theta times sine theta all over g. So my range is equal to 2 v0 squared over g times cosine theta times sine theta. But if you go back to your trig relationships, you will find that the cosine of theta times the sine of theta is the sine of 2 theta all over 2. And so this is equal to v0 squared sine 2 theta over g. Now this 2 theta really is important. If you recall your trig relationships, this is my angle theta in here in the first quadrant, then the sine of theta is opposite over hypotenuse. But if I go over here to the second quadrant, this angle beta has a sine, and the sine of beta is equal to opposite, which is actually this side right here over the hypotenuse. So if this is some angle alpha, then the sine of beta is equal to the sine of alpha. Remember, the sine in the second quadrant is positive. This is referred to as the reference angle of beta. And the sine of beta and the sine of alpha are the same. So what makes this important is that if I take the sine of 2 theta, if that becomes an angle when I double it in the second quadrant, this will have a reference angle. And so what ends up happening is the sine of 2 theta is equal to the sine of, say, this alpha. Let's think about that range equation again. If I have a projectile that has an initial theta equal to 30 degrees, the range equation involves the sine of 60 degrees, double that. But if this is 60 degrees, then this is 120 degrees. But that's double the 60 degrees. So the sine of 60 degrees equals the sine of 120 degrees. Now let's try another angle. What if theta was equal to 10 degrees? Then the range equation involves the sine of 20 degrees. But if this is 20 degrees, then there's another angle here, and that angle would be 160 degrees. So the sine of 20 degrees equals the sine of 160 degrees. But 20 degrees means I came off at an angle of 10 degrees. 160 degrees means my original theta was equal to 80 degrees. So notice what's happening here. If I take these two angles and I add them together, I get 180 degrees. If I take the 30 and the 60 and I add them together, I get 90. If I take this angle and I add them together, I get 180 degrees. If I take that angle and that angle together, I add them together, I get 90 degrees. What that means then is that I have a range at a given angle theta. I'm going to get the same range at an angle theta that's complementary to the first. So what that means is if I shoot an object at an angle of 10 degrees, I'm going to get to the same place as if I shot it at an angle of 80 degrees. If I shoot an object at an angle of 20 degrees, I'm going to get to the same place as if I shot it at an angle of 70 degrees. So they'll be at the same location. The only difference will be the trajectory. So if this was an angle of 30 degrees, it's going to end up landing over here. I'm going to get to the same place if I went at 60 degrees, except I'm going to go higher, and I'm going to take longer, but I'm going to land at the exact same place. So there's always two angles that will give me the same range. Again, starting and ending at the same level ground. There will always be two angles that will give me the same range. One will be a low trajectory and take a short amount of time. One will be a much higher trajectory and take a longer time, but they'll both land at the same spot. Let's work an example. So let's say I have a trebuchet, which was an old medieval war machine, and it was used to throw rocks at walls. So let's assume this trebuchet shoots a rock with an initial speed of 50 meters per second. So I'm just going to start my given. My given is that I have an initial speed of 50 meters per second, and I'm told that it shoots at an angle of 36.9 degrees. So theta is equal to 36.9 degrees. Now one thing you want to keep in mind, a 36.9 degree angle is part of a 3-4-5 triangle. So this is the angle theta here. And I like using that angle because it's easy to work with. So the question is, what is the speed of the stone if it hits the wall 200 meters away? So my distance, x, is 200 meters. Now I'm not using the term r for range because I'm not ending up at the same height. It's a different height. In fact, that's question B. What is the rock's height? And then, is it on its way up or on its way down? So the wall is 200 meters away. And what do I want to know? I want the final y value when it hits the wall. And I want to know, is the velocity on the way up or on the way down? If it's on the way up, the y component of the velocity will be positive. If it's on the way down, the y component of the velocity will be negative. So if I draw a picture, my trebuchet is going to shoot a rock at the castle wall, and the trajectory is going to look something like this. Or it could be on the way up, so let's find out. So I have a 3-4-5 triangle. My velocity is 50 meters per second. So what that means is my initial velocity vector is going to be 40 meters per second. That's 50 meters per second times the cosine of 36.9. But the cosine of theta is 4 over 5. So 4 over 5 times 50 is 40 meters per second. So that's in the I, plus 30 meters per second in the j. You can do the mathematics if you want on your calculator, but I suggest you learn that 3-4-5 relationship. There's my velocity, x and y component. I'm interested in what's happening when the wall is being hit at a distance of 200 meters away. So I'm using projectile motion. That's my principle. And so I know that x equals x naught. Let's put my y-axis here, my y-axis here, my x-axis there. My initial x then is 0. So x equals 40 meters per second times t. But that's going to be 200 meters when it hits the wall. So t is equal to 5 seconds. Then the question is, what is y? Well, y is equal to y naught, but that's 0, times 30 meters per second t minus 1/2 g, and I'm going to use 10 meters per second squared for g just because it's easy to work with, t squared. But I know what t is. T is equal to 5 seconds. So this is 30 meters per second times 5 seconds minus 1/2 10 meters per second squared times 5 seconds squared. And so that's 150 meters. Seconds cancel. And this would be half of 10 is 5 times 25. So that's minus 125 meters. So 25 meters. So it strikes the wall at a height of 25 meters. Then the question is it on the way up or on the way down? Now remember your velocity equation. Velocity was equal to initial velocity plus acceleration times time. But we're looking at the y velocity. So the initial y velocity, the acceleration in the y direction. So v sub y is equal to 30 meters per second minus the acceleration, which is the acceleration due to gravity. Well, plus the acceleration due to gravity, but that's negative. And I'm using 10 meters per second squared times 5 seconds. And so this is 30 meters per second minus 50 meters per second equals minus 20 meters per second. So it must be coming down when it hits the wall. It's on its way down.